As you see, we didn't cover a lot of things from this sampling chapter, but for me it is finished. So there are only two fundamental issues that you have to be careful about in terms of this sampling business. One of them is the knowledge of the Nyquist rate to avoid aliasing. So Nyquist rate, sampling frequency, aliasing, those concepts are the first important issue that you have to be aware of. The other one is the one that we have just seen in the last hour, which is the discrete time or computer processing of continuous time signals. And the way to do it is, again, as I repeat, sampling the system. Okay, you capture the low pass portion of your system, which is within the range of your bandwidth of your signal, and then repeat it. When you make a replication of those things, you get a sampled system. That sampled system corresponds to the system that must be implemented in the computer using your programs. And the output, you give it to a digital to analog converter, and the whole system, the overall system, acts like your original continuous time system. So these two issues are the only two issues that you must be careful in your exams, including the second midterm or the final or everything. Okay. Therefore, we're not interested in the other issues, and now we can continue with the next chapter. The next chapter is Laplace transform. And for the years that I have been teaching this course, I find this chapter to be the easiest to explain and the easiest to understand for the students, because probably you already know it. You have been using it in differential equation solving, sort of. And it makes a lot of sense. It's even easier than the Fourier transform itself. But it's an extension of the Fourier transform. By the way, there is one difference between the way to solve the differential equations and the way to solve the Laplace transform problems in this chapter, because this one is the so-called bilateral Laplace transform, two-sided Laplace transform. We will see what it means. And the Laplace transform, the S parameter that you have been using in differential equations courses, are the unilateral Laplace transform or single-sided Laplace transform. Those unilateral transforms require the knowledge of initial values. You remember that? You had to know the initial values of your signal in differential equations. Now, we don't need that in the bilateral case. So the way to approach the problems will be slightly different, but still quite similar. Now, what is the thing that motivates the Laplace transform? Do you remember this phenomenon? When e to the j omega t goes into a linear and time invariant system, the output was h of omega times e to the j omega t. Remember this phenomenon? So the complex exponential, a sinusoid, comes into a linear time invariant system. The output is the same complex exponential, scaled according to its frequency. And that according to frequency is the frequency response, h of j omega, which was formulated by the formula easily as the Fourier transform of h of t, if h of t is the impulse response, for instance. So we know this, but it's not complete. This similar phenomenon exists not only for e to the j omega t, but for other signals like this. So the input is not e to the j omega t, but it is e to the sigma t, e to the j omega t. In other words, the exponent angle term is not totally imaginary, which causes an oscillation, but it has a real part of sigma as well. This real part, if sigma is greater than 0, it may cause an expansion, a blow, so the oscillation will grow. Or if sigma is less than 1, less than 0, sorry, if it is negative, then it will be a decaying exponential, a damping exponential. But nevertheless, for all such terms, including the sigma, positive or negative, whatever, we have the same way of behavior. This will be h of sigma plus j omega. So the response will be scaled according to the value of sigma and according to the value of frequency altogether, times e to the, sorry, not j, e to the sigma plus j omega t. Okay. This is a more generalized way of imagining or considering the input-output relation. Do you remember what I call such signals for LTI systems? These are LTI systems because they have impulse responses. They were called the eigensignals, I said, because they look like the eigenvalue, eigenvector situation. It's like the eigenvector. This one into the geometry is like an eigenvector of a matrix. What was the property of an eigenvector for a matrix? Let's say that the matrix is A and the eigenvector is V. If I apply this eigenvector to this matrix, then the output will be the same as the eigenvector, scaled on with an eigenvalue. So the input is V, the output, the input to the system is V, the output of the system is again V, only scale. That is the situation that we have here. The input is e to the j omega t, the output is e to the j omega t, only scale. That's why they call it eigensignal. Now, e to the j omega t is not the only eigensignal we are saying in this chapter. We are saying that e to the sigma plus j omega t is also an eigen signal. And it doesn't change either. It goes up the same on the scale. Now we can deduce something from there, including the real part, not only the imaginary part, not only the harmonic, the oscillation part, but the real part is also inserted into the equation. And sigma plus j omega is given a new variable called s, which is the Laplace variable. Now that Laplace variable, if you call s is equal to sigma plus j omega, induces the Laplace transform, which is given here, h of s. So h of s is the Laplace transform of h of t. H of j omega is the Fourier transform of h of t. So what is that Laplace transform definition? You can extract this formula by solving this input-output relation and convolving h of t with e to the sigma plus j omega t. You can do it. Just try to convolve this signal with h of t and try to express it like that. And over there you will find, or you will reconstruct the formula for the Laplace transform like this. It truly resembles the Fourier transform. It's in fact the same as the Fourier transform. E to the minus st dt. Nothing different. Because the Fourier transform was h of j omega is equal to integral h of t e to the minus j omega t dt. Every j omega is replaced by s, which is sigma plus j omega. So instead of j omega, we put sigma plus j omega and say it to be equal to s. And that's an easy definition. Clearly, this definition of the Laplace transform is not only valid for systems or system responses, it's also valid for any kind of a signal. We can say that x of s in general is the integral, infinite integral of ht e to the minus st dt. So this is the famous, celebrated Laplace transform. And since it doesn't look imaginary with a j or anything, usually students better memorize this However, it's a little bit complicated. It's even more complicated than the Fourier transform because S now is not real. It is sigma plus j omega. J omega is the thing that we already have. So, for example, we can write things like this. What is x of j omega? It is equal to x of s, evaluated at s is equal to j omega, which is equal to x of s, evaluated at sigma is equal to 0. So these two definitions are equivalent. And when you have the Laplace transform, therefore, the way to propagate to the Fourier transform is quite easy, as long as it exists, unfortunately. Because x of s, the Laplace transform, has one extra condition on it. It is not only this formula that we have for the expression of the Laplace transform. We need to express where, for what values of sigma that integral converges, and for what values of sigma it doesn't converge. It may or may not converge, unfortunately. So the Fourier transform exists if in the region where s is equal to j omega or sigma is equal to 0, this x of s, if it exists there, then that existed thing corresponds to the Fourier transform. That existence will be clearly understood with some examples. We are just starting with some examples now, but before that, well, anyway, the inverse for Laplace transform definition should also be given to you, but it's a little bit complicated for the time being. So let's start with the examples first, and then later on we will continue with the inverse Laplace transform. In other words, if you have x of s, how are you going to find x of t? It's not an integration over omega d omega anymore, because we don't have omega, we have s. So that's a strange inversion that we need to cover. Anyway, we will see that later. Let's start with some examples now. Let's start with the trivial example, our famous e to the minus at u of t. This was an example where we have also found the Fourier transform, if you remember, the first example, because its integration is easy. So x of s is equal to, let's write the formula. The infinite integral x of t e to the minus st dt, and that is from minus infinity to infinity e to the minus at u of t e to the minus st dt. Okay. This u of t inside our integral forces the integration to start from 0 and go to infinity, because u of t is 0 before t is equal to 0. So I'm going to write the integral like this, from 0 to infinity, and I'm not going to write u of t inside the expression, because it's 1 from 0 to infinity. And I have e to the minus, in parentheses, a plus s t dt. Okay, do we agree with this? I combine the two exponents. And this integration is an exponent integral from 0 to infinity, which can be carried out just like the method that we did for the Fourier transform, to find it as 1 over s plus a, or a plus s. Okay. It's equal to minus 1 over s plus a e to the minus a plus st. Okay, if you're not happy with the abrupt solution, maybe I should do a few more steps. Minus 1 over a plus s e to the minus a plus st from infinity to 0. Okay, and at infinity, at t is equal to infinity, e to the minus a plus st, as long as the exponential's real part is decreasing, will decrease to 0, e to the minus infinity, in other words. E to the minus infinity is 0. So it will be minus 1 over a plus s in parentheses 0 minus, at 0, e to the 0 is 1. So it is in minus 1 over a plus s parentheses 0 minus 1. And that's why it is 1 over a plus s. I say okay, but you must be a little bit worried about the convergence. I said that e to the minus a plus st at infinity, t is equal to infinity, must be 0. And it is equal to 0 under certain circumstances. It depends on the real part of s. There was a sigma plus j omega, you see. The j omega is not important, it's just oscillating. But a plus sigma, that thing, must be positive so that the integral will go to 0, or the value will go to 0 at t is equal to infinity. We will come back to that. Let's assume that it goes down to 0 and we have a plus s. 1 over a plus s. By the way, do you remember that x of j omega was 1 over a plus j omega? Just check your notes. That's something that we have already found. So the substitution of j omega with an s is safe. In fact, if you have a Fourier transform of something, and I told you that you must bring your typical transform pairs and properties tables from the book, photocopies of those. Just look at the Fourier transform table. If there is a Fourier transform of that signal that I'm asking you, and I'm asking you to find the Laplace transform, and you find the Fourier transform, then you're safe. Just replace every j omega with an s, and that will be the Laplace transform without any calculations. So if you have 1 over a plus j omega, then the Laplace transform is clearly and obviously 1 over a plus s. But we have now another example which imposes the problem e to the minus at u of sorry, I need to find, minus e to the minus at u of minus t. Suppose this is our new signal x of t, and I'm again asking you the Laplace transform. The Laplace transform is x of s is equal to, from minus infinity to infinity, minus e to the minus at u of minus t e to the minus st dt. Okay, that's the formula. And u of minus t, let's take the minus sign outside, makes the integral limits to go from minus infinity to 0 now. Okay? Because it's u of minus t is 0 for all positive t's. For all positive t's, u of minus t will be 0. So it's from minus infinity to 0, e to the a plus s in parentheses d dt. Yeah, with a minus sign in the exponent. And when you evaluate this thing, if it converges at minus infinity, you have to make sure that for certain sigma values it must converge at t is equal to minus infinity, and if it converges down to 0, and in that case you will find this integral to be equal to 1 over a plus s again, if it converges. So, do you see the problem now? It's the same Laplace transform. And I have to put, if it converges, here too. So the Laplace transform of e to the minus at u of t is 1 over a plus s, and the Laplace transform of minus e to the minus at u of minus t is also 1 over a plus s. So, Houston, we have a problem. Because a transformation is one-to-one. You must always have a unique inverse transform for a proper transform. In other words, you must always give me the answer to this question. If x of s is equal to 1 over a plus s, what is x of t? And suddenly you say that it is either minus e to the minus at u of minus t or e to the minus at u of t, which are completely different signals. One of them is left-sided, the other one is right-sided. One of them is positively decaying. The other one is negatively increasing, so that it decays to the negative side. So they are two different signals. And what is the difference between them? How are we going to differentiate between them? Now let's take this one. This one, if it converges, case. Minus 1 over a plus s. So case 1. Minus 1 over a plus s e to the minus a plus s t from 0 to infinity. What is this? When does it converge? If it converges, I said. When does this converge? Converges if a plus s, or let me write it like this, the real part of a plus s is positive. Because if a plus s is a positive in real magnitude, then even minus that thing times t will decay. Okay? Is that okay? This one converges only for this thing, the real part of it, to have a positive value, so that even minus of that positive times t at t is equal to infinity will converge to 0. So real part of a plus s must be greater than 0, and real part of a is a. Real part of s is real part of s must be greater than 0, or real part of s must be greater than minus a. You can also write it like this: sigma is greater than minus a. If sigma is greater than minus a, sigma is the real part, then a plus sigma will still be positive. For example, let's say a is equal to 2, the value of a is equal to 2, then sigma must be greater than minus 2. If it is minus 1, 2 plus minus 1 will be still positive. It will be 1, and it will still decay. You can think of it like that. So this condition, or this condition, is a secondary or auxiliary information that must be accompanying the Laplace transform itself. What was the Laplace transform? The Laplace transform was 1 over a plus s. X of s was that. But you must give me one second information, and that second information is this or this. Either way you can say. The real part of s must be greater than minus a. Whenever you say it so, I can say that, okay, then I know the inverse Laplace transform. It must be e to the minus at u of t. It corresponds to that. However, if the second case is case 2 is valid, then in the second case, what was the integral? It was minus from minus infinity to 0 e to the minus s plus a t dt, and that is two minuses will cancel each other. It will be 1 over s plus a e to the minus s plus a t from minus infinity to 0. Now this thing, if it converges at minus infinity, if this thing converges at minus infinity, then s plus a must have a real part to be what? Negative this time. Because if it is negative, then minus of that negative will be positive. So it will be a positive going exponential, but I'm looking at it at minus infinity. At minus infinity it must decay. So the situation is just the opposite of the other one. Real part of a plus s must be negative. Or a plus real part of s must be negative. Or real part of s is less than minus a, or similarly sigma is less than minus a. This one or this one, whichever you say. And as you see, it's just the opposite of the other one. In the first case, we said real part of s is greater than minus a. Now we say real part of s is less than minus a. So what is this critical point of minus a? There is a critical point. It is minus a. If real part is greater than that, it corresponds to a signal. If real part of s is less than that, it corresponds to the second signal of interest. So what is that a or minus a? It's not a, it's minus a. What is the significance of minus a in this Laplace transform of, okay, let's write it here. Laplace transform is x of s is equal to 1 over s plus a. Can you see the significance of minus a? No. I'm asking for the significance of this entity, minus a. Minus a is something important with respect to this equation. It is the so-called singularity point of this x of s, because when s is equal to minus a, as you see, the denominator becomes 0. That is the singularity point, which is also known as the pole. It is the pole of the system. A pole is a singularity point where the Laplace transform diverges to infinity. Or you can think of it like this. If it's in the form of a numerator over denominator, it is the 0 of the denominator, the root of the denominator. So x is equal to minus a is a root of the denominator. A root of the denominator for such rational things. So the critical way to represent properly the Laplace transform is by giving the Laplace transform. So you must say x of s is equal to whatever, the Laplace transform, and real part of s is greater than something, or real part of s is less than something. There are in fact other things like, or real part of s is greater than something but less than something. In 3 different ways you must give me an expression. With the combined expressions, it has a meaning. It constitutes the whole Laplace transform. The Laplace transform by itself is not only x of s. It must be accompanied by either of these things. For example, if you say x of s is equal to 1 over s plus a, and sigma is less than a, or real part of s is less than a, is less than minus a, sorry. Suppose you say this and that is a Laplace transform. which has a unique inverse Laplace transform, and that inverse Laplace transform is minus a to the minus at u of minus t. If you give me the Laplace transform like this, x of s is equal to 1 over s plus a, and real part of s is greater than minus a, that's a Laplace transform. And the corresponding time signal is e to the minus at u of t, the first example. So these things are critical, these expressions, or these expressions. And these expressions have a name. The name is called region of convergence, and abbreviated as ROC. Therefore, a true Laplace transform has x of s and region of convergence together. You must tell me what the region of convergence is. Now, the region of convergence is not a threshold. It looks like a threshold. Real part of S is greater than something, real part of S is less than something, or in between something. So on the line of real axis, it is between 2 points. Then why am I calling it a region? The region terminology comes from the Laplace to be considered in a plane, not on an axis like this. And the thing that I'm drawing here has a unique name. It is called the S-plane, or the Laplace plane, you can say. This is the Laplace plane that I'm drawing. In the Laplace plane, the horizontal axis is the real part of S, which is sigma, and the other is the imaginary part of S, which is j omega. So sometimes people call that the horizontal axis is the sigma axis and the vertical axis is the j omega axis. You can say it like that as well. And now you must indicate the singularity points on this plane. Let's locate them. For this previous example, what was the singularity point? S is equal to minus a is a singularity point. We mark that on this plane. And remember that A is real, whereas the vertical axis is an imaginary axis. So where are you going to insert or mark S is equal to A? S is now two-dimensional, the real part and the imaginary part. So S is equal to A is minus A is where? It's on the real axis. Let's assume that A was positive, so minus A is here. It's just an assumption, depending on the value of minus A. I put a cross there, and the cross indicates a pole. It's always like that in your books. It is indicated like this. And independent from the imaginary part of that, regardless of the imaginary part, the real part becoming minus A is the boundary of our plane for the region of convergence. So we put a boundary, we draw a boundary like this. Now that boundary bounds our region of convergence. If region of convergence is real part of S greater than 0, minus A, greater than the pole, then we just draw the region of convergence like this. We trace that portion corresponding to real part of S greater than minus A. So the real part's axis goes towards the right hand side, and the imaginary can be anything. So this is the region. What I draw here is the region of convergence. Okay, that's how you will draw. If it is greater than minus A, it is to the right hand side. If it is less than minus a, it will be to the left hand side, of course. This is j omega, this is sigma axis. Again, let's put a pole at here. Then it could be like this. The region of convergence may be like this for real part of S less than minus a. It is to the left hand side of minus a. This could be the region of convergence. Therefore, that's how you define it. In many of the questions, I ask you, I will ask you to draw the region of convergence. Not only give me real part of S is less than minus a, which is a correct answer, but if it is, for example, 10 points, when you write real part of S is less than minus a, I will give you like 7 or 8 points, because I will also ask you to draw it on the S plane to illustrate where it corresponds to. And therefore, you have to dash that region like this. That is the region of convergence. Now, looking at these two alternative regions of convergences, I will ask you a question. Which of these, with the same Laplace transform of 1 over a plus s, which of these have a Fourier transform? Because one of them doesn't have a Fourier transform. The Dirichlet condition is violated for one of them. It is not violated for the other one. In fact, you already know the answer, because e to the minus at u of t for positive a, which means for negative minus a, has a Fourier transform of 1 over a plus j omega. The Fourier transform exists for that. So, which of them is that? The top one or the bottom one? It is the top one. For this one, e to the minus at u of t for a greater than 0, which means for minus a less than 0, and the region of convergence for that one is real part of s is greater than minus a, that one. Okay. So for this one, the Fourier transform exists. And there is an easy way to see why it exists in this shape. Because the region of convergence includes the j omega axis. The Fourier transform is equal to S is equal to j omega. You remember that. S is equal to j omega means sigma is equal to 0, and all we have is this axis. Only along that axis, that is where we have the Fourier transform. The others, along the region of convergences, it is the Laplace transform. The Laplace transform may exist here, 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 whatever. But the Fourier transform is the Laplace transform only for this axis, which is only for S is equal to j omega axis. And it must be staying inside the region of convergence for its existence. If it doesn't stay in the region of convergence, the j omega axis, you say that the Fourier transform doesn't exist. Okay? It's as simple as that. But it is valid in this example. The Fourier transform for the top shape exists if A is positive. Notice that. If A is positive, then minus A will be here, and to the right of it will include the j omega axis. What would happen if A is negative? It's just the opposite. If A is negative, then minus A will be somewhere here, somewhere on the right hand side. And to the right of that will not include the j omega axis. However, minus A will be here for the other case, and to the left of it this time it will include the j omega axis, and then you will say that minus e to the minus at u of minus t has a Fourier transform if A is negative. So regardless of whether it is right-hand-sided or left-hand-sided, don't worry about being right-hand-sided or left-hand-sided. Just worry about whether this thing, this axis, is included in the region of convergence or not. If it is included, then you say the Fourier transform exists. And guess what? The existence of the Fourier transform, if it is the Laplace transform of not a signal but a system, h of s, we are putting the region of convergence poles and drawing the region of convergence for a system, h of s. The existence of the Fourier transform means stability of the system. If j omega axis is inside the region of convergence for a system, then you say that the system is stable. And that's perhaps the most fundamental thing that you will cover in the second semester's Introduction to Control Systems courses. In the next semester you have that. So there is a stability problem there for the control systems. Do you remember that when I asked you linear time invariant causal stable thing? For the stability, bounded input, bounded output stability, I didn't teach you any systematic way if the system is difficult to explain. If you have the impulse response, of course, the magnitude sum of the impulse response must converge. That's a rule. But now you have a better tool to analyze the stability of linear and time invariant systems. It's the Laplace transform. Just evaluate the Laplace transform. Put the pole or the poles, there may be more than one pole, and indicate the region of convergence. If that region of convergence has or includes the j omega axis, you say that the system is stable. It's a very systematic way of categorizing stable and unstable systems using the Laplace transform. Okay. Now, it was a little bit difficult for us to decide whether this is the pole. It's easy to understand because it's the root of the denominator. S is equal to minus A is a pole, we know. But is the region of convergence to the left or to the right for our case? It was a little bit difficult for us to see what's going on. We had to indicate the exponents, etc., and see whether it converges or not. But there is a shortcut for guessing whether it is to the right of the pole or to the left of the pole, the region of convergence. And it's as simple as this. So let's write it. Decision of real part of S greater than pole or real part of S less than pole. How do we decide on that? The decision is according to the side of the signal or sidedness, let's say. E to the minus AT U of t. What sided signal is that? I have to say that it is right-sided. It extends from 0 to infinity. So if it is right-sided signal that you have, then it is to the right of the plane, which is like this shape, to the right of the pole. If your signal is a left-sided signal expanding towards the left, like minus e to the minus at u of minus t. U of minus t is left-sided sequence. Therefore, you have to choose to the left of the pole, like this shape. As simple as that. You don't have to worry whether this integral here converges. Where does it converge? Because it's a little bit complicated. It's even complicated for this first order system, which is the simplest system. For more complicated cases, you have to just decide whether the region of convergence is to the right of the pole or to the left of the pole. Where? You just have to look at the signal. Is it right-sided signal or left-sided signal that you have? If it is right-sided signal, you say it's to the right of the pole. If it is left-sided signal, to the left of the pole. As simple as that is the decision. Okay, now Okay, we will end the lecture here, but before ending, let me say a few concluding remarks. This is a first order system, and the order of the system is defined by the number of poles. If it is 1 over s plus a, there's one pole, it's first order. If the system has more than one pole, multiple poles, it will be second, third order, whatever, according to the number of poles. And for each pole, along the real axis or along somewhere else, they can even be not necessarily on the axis, the decision will be either to the right of the pole or to the left of the pole for each pole. Then we have to intersect those spaces, those regions. Suppose it is to the right of -4, intersection with to the right of -2. What is the combined region of convergence? Yeah, it must be to the right of -2. That is the intersection of the both cases. Let me ask you another question. If it is to the right of -2 and to the left of +1, where is the intersection? It is between -2 or 4, whatever I said, and 1. It's not a region extending to infinity. It's a region, it's a strip of a region, bounded from the right and bounded from the left. Those cases will also be available to us. We will see a lot of examples of these things, and it's quite easy, as you see. Once you get x of s, you will evaluate the poles. According to the poles, you will see to the right or to the left, and you define the region of convergence. X of s plus the region of convergence, you put it inside a box and put a check mark and get 10 points from this question. It's as simple as that. So let's stop at this point. We will continue next week.